Welcome to 9.3, where we're going to be talking about resistance within a circuit. So first, resistance. It's defined by its name. It's the ability of an object to resist the flow of charge. So over to the right here, you see an object. Every object has a number of electrons or charges inside the object. When more charges are pumped into that object, the difficulty to move through is based on the resistance. The difficulty of these charges to get from one side to the other is based on the resistance of the substance. Now, naturally, the electrons are going to resist more charges coming through. And the amount that they resist, the force of more charges to move through the wire, that's the amount of resistance that's going to be present. So the resistivity is actually different than the resistance. Resistivity, or this little curvy p, which is called a rho, is a property of a given type of material, and it is based on the material. So in your reference tables, and you can see it right here, you've got a chart of the resistivities of various materials at a certain temperature, 20 degrees C. Notice, based on this chart, the unit for resistivity is an ohm meter. And you have a bunch of different values that are based completely on the material that you are using. So resistivity is one factor that will determine how resistive, or the resistance of a wire or of a material. But there's two other components that are also going to affect how what the resistance is of a material. The second is the cross-sectional area of the substance, and that's what you can see in this beautiful picture down here. Each wire, every substance, has a width or an area. If you take a slice of that, that's what's popping out here, and that slice, looking at it from the front on, is an area of a circle. So if you want to figure out the cross-sectional area of something, you can just use the equation for finding the area of a circle. Cross-sectional area is going to affect how resistive a material is. The bigger the space, so in other words, the bigger the cross-sectional area, the easier it is for charges to fit through and to flow, so the less resistance will be present. And then the third factor is the length of the wire, or of the substance. The longer the substance is, the more difficult it is for charges to flow through, because they have to flow through a farther distance. So now that we've talked about the three things that are related to the resistance, let's write an equation for it mathematically, where R represents the resistance, the letter rho represents the resistivity based on the material, we have L for length and A for area, and you can actually find this equation right in your reference table. Resistivity is ohm meters. Length, we're going to measure in meters. And area is what A stands for. So let me give you this. Length, our measurement is meters. And remember, area is that cross-sectional area. And that's going to be measured in meters squared, since it's an area measurement. Now, if you do a little bit of math with the units here, you can actually figure out that if we were to put in the units for each of our components here, the meters end up canceling out, and you're left with an ohm, spelled O-H-M. That is the unit for resistance, or for our R here. Resistance is going to be measured in ohms. So let's do a couple examples using our equation. Here we've got a 10-meter long copper wire. The material is important, at 20 degrees C. We want to know the radius of the wire. They give us the radius of the wire, and it's 1 times 10 to the negative 3 meters. Let's determine the cross-sectional area of the wire. So if this is my wire, I want to determine just the area of the flat part of the wire if I were to cut the circle off. Well, I know to find area, it's pi r squared. So I'm going to plug in our values. We've got pi. I'm going to multiply by the radius, 1.0, times 10 to the negative 3 meters. That's squared. And if I multiply that out, I get 3.14 times 10 to the negative 6 meters squared. Now I can take this value for the area and I can calculate the resistance of the wire. Where I know to solve for resistance, it's rho L over A. And I can plug in, since this is a copper wire, I can go back to my chart and I can find the resistance for copper. I'm sorry, the resistivity for copper on the chart. I can pop that right into this equation. 1.72 times 10 to the negative 8 ohm meters. And I can multiply by the length of the wire, 10 meters, and divide by the area value I got above. When I multiply that all out, I end up getting a value of 0.05 ohms for the resistance of our wire. Second question, see if you can do it on your own first. Check my answer when you're done. I've got a 3.5 meter long wire with a cross-sectional area of 3.14 times 10 to the negative 6 meters squared, and it has a resistance in ohms. I want to determine the resistivity, remember, which is that curly P, that's the rho of the wire, and I want to determine the material. So I'll set up my equation, rho L over A. I'm going to plug in what I've got. If I solve that all out for rho, I end up getting 5.6 times 10 to the negative 8 ohm meters. And if I take a look back at the chart on my reference table, I will see that that is the same value for tungsten. So I know based on its resistivity, this material must be tungsten. Now there's another interesting point we haven't talked about with resistance, and that's temperature. And some of you saw this in your labs. As the temperature within a resistor increases, the resistance of that wire is also going to increase. So notice back in our chart in your reference table that all these resistivities based on the material are set at 20 degrees C. That's because these numbers will vary if I change that temperature. If I increase the temperature, that resistivity is going to go up. So the question is why? Well, think about electronics getting hot while you use them, something like your computer or your cell phone. If it's charging, if you're using them a lot, sometimes the back gets hot and you get nervous. Oh no, the resistance is too high. Well, why? Electronics don't work as well often when they get hot. They overheat and that can do damage to the electronic components. Why is that the case? Well, when you increase temperature, you're actually increasing the kinetic energy of the molecules. The molecules are moving faster. And therefore, when things are moving faster, it's harder for your electrons or for your current to get through the material. Because there's so much energy, they're moving so quick, it is harder for the electrons to get through, so your system doesn't work as well at a high temperature. However, we almost always talk about, oh, resistance is bad, resistance is bad. Well, sometimes you want resistance. Some systems run on have something having a high resistance. For example, a toaster oven. If you're making toast, you might want your toaster oven to heat up. Probably that's why you're using it. So actually, it's a great thing that the toaster oven is going to have a higher resistance. And those nice little wires that show up in your toaster oven that you might see kind of glowing a little red, those are resistors. And those are increasing resistance with increasing heat, and that's what's able to toast your toast. Now, toaster ovens are often made out of nickel. You might say, why? Look at the resistivity of this material. It's a lot higher than the resistivity of copper, which means it's going to produce heat a lot more quickly than a copper wire, which is great if you're trying to heat up toast. It all depends on your purpose. If you're trying to charge your cell phone or use your computer, probably high heat is not good for your circuit. So let's take a look at 9.3, Ohm's law. Ohm's law tells us a relationship between resistance and current and voltage within a circuit. Current and voltage, or current and potential difference, are the two components we've talked about so far. We know that as resistance increases, the current flow in an object decreases, meaning that these quantities are inversely related. And as the potential difference increases, the current flow of an object also increases, showing that these are directly related. So that allows us to write an equation for Ohm's law based on what we know above, and you'll see Ohm's law is V equals I R, which you might have seen before. Simple equation. Your reference table puts it R equals V over I, and that just shows you that if I increase V, the radius is also going to increase. Since the current is on the bottom, if I increase that, the radius will decrease. That is Ohm's law. All these components we talked about, but let's just go through it one more time. V is your potential difference. That's going to give you volts. That's your unit. I is your current. That's in amps. A volt per amp is an ohm, which is what we measure resistance in. There's your SpongeBob toaster in the wrong spot. And here's a quick example. There's 3 of them. Take a second, see if you can do these based on Ohm's law using your reference table, and then come on back and check your answers. So we've got a 12-volt battery, and it causes a 2-amp current to flow through a copper wire. What is the resistance of the wire? Well, I take V equals IR. I might switch it around. R equals V over I. I'm going to plug in what we have. 12 volts over 2 amps, and I end up with a nice 6 ohm resistor. Let's take a look at a second problem. You've got a 120 volt outlet, and it applies a difference in electric potential energy across a toaster with resistance of 14 ohms. Let's calculate the current. So we know that V equals IR. I know I have 120 volts. I'm looking for the current, and the resistance is 14 ohms. That leaves us with a very nice 8.6 amp current. Now this next one's got 2 parts to it. We've got a charge of 3 coulombs moving through a circuit with a resistance of 6 ohms for 0.5 seconds. I want to know the potential difference in the circuit, which means we are looking for V. So I'm going to set this up, V equals IR, and I know the ohms are 6, I know that's the resistance. I actually don't have current yet, but I do know that I can take a second and I can find current using our other knowledge that current is a flow of charge over time. So I know that we have 3 coulombs passing through every 0.5 seconds, which if I solve that out will give me a 6 amp current, which I can plug back into our equation, 6 amps, so that I can arrive at a 36 voltage potential difference.